Corrosion. The quiet force that eats every plant, every pipeline, every storage tank, every hour of every day. Let's see how it starts, the forms it takes, how we judge severity, and how we find it before it finds us. Why does it matter? Because corroded metal simply disappears into the environment, and with it goes the pressure boundary. The results: leaks, ruptures, fires, spills, and unplanned shutdowns. The global bill is estimated at $2.5 trillion a year, and studies show a large share of that is avoidable with known corrosion control practices. Corrosion never sleeps, so inspection can't either. At its heart, corrosion is electrochemistry, a natural battery. Four elements must all be present. An anode, the spot where iron atoms give up electrons and dissolve as ions, that is the damage. A cathode, a nearby spot that consumes those electrons, protected, unharmed. An electrolyte, water with dissolved ions, even a thin condensed film is enough. And a metallic path, the steel itself, carrying the electrons from anode to cathode. Iron ions meet oxygen and water and become rust, occupying 6 times the original volume. Remove any one of the 4 elements, and corrosion stops. That principle is behind every defense we have. What controls the speed? Moisture first, no water film, no cell. Oxygen feeds the cathode reaction. Temperature accelerates everything, reaction rates roughly double for every 10 degrees. Chlorides and salts break down protective films and open the door to pitting and cracking. Acidity attacks steel directly. And velocity strips the films that protect the surface. Severity is never one number, it is environment, multiplied by temperature, multiplied by time. Corrosion wears many faces. Uniform attack, even wall loss. Pitting, deep local holes. Crevice corrosion in gaps and under deposits. Galvanic attack where dissimilar metals touch. Stress corrosion cracking, brittle cracks from stress plus chemistry. Erosion corrosion where flow strips the surface. And the stealth killer, corrosion under insulation. Diagnose the form first, each has its own cause, its own look, and its own countermeasure. Uniform corrosion is the most common and the most honest. The whole exposed surface retreats at roughly the same rate. That makes it easy to measure. Ultrasonic thickness readings give you the wall today, and repeated readings give you the rate in millimeters per year. From there, remaining life is simple arithmetic. The danger is not the mechanism, it is failing to measure it. Unchecked, a pipe quietly thins until the pressure wins. Pitting is the opposite, tiny weight loss, catastrophic consequence. It starts when chlorides break down the passive film at one microscopic spot. That spot becomes a small anode surrounded by a huge cathode, so instead of spreading, the attack bores straight down. And it feeds itself, the chemistry inside the pit stays acidic, accelerating the attack, we call it autocatalytic. Stainless steels and aluminum, the alloys that rely on their passive film, are the classic victims. With pitting, the metric that matters is depth rate, not weight loss. A wall that is 99% sound can still leak tomorrow. Crevice corrosion hides in the gaps, flange faces, gasket edges, under deposits, lap joints, tube-to-tube sheet crevices. Water wicks into the tight gap and gets trapped. The oxygen inside is consumed by corrosion and cannot be replenished, so the crevice becomes anodic to the bold surface outside. Attack grows inside the gap, out of sight. Stainless steels, starved of the oxygen their passive film needs, suffer most. The design fix: eliminate gaps, use full penetration welds, and keep things drained and clean. Galvanic corrosion needs 3 ingredients: 2 different metals, electrical contact between them, and a shared electrolyte. The less noble metal becomes the anode, and sacrifices itself to protect the nobler one. The worst-case geometry: a small active area coupled to a large noble one, like a few steel bolts in a stainless assembly, the bolts perforate fast. The fixes are elegant: electrically insulate the joint, or choose metals close together in the galvanic series. Same physics as a sacrificial anode, except here, your equipment is the anode. Stress corrosion cracking is the sudden one. It needs all 3 at once: a susceptible alloy, a specific environment, and tensile stress, from service or left over from welding. The classic pair: chlorides on austenitic stainless steel, and caustic on carbon steel. The result is branched cracking with almost no metal loss. The part can look perfect and fail the same day. There is no thinning to trend, so detection relies on the right NDT, dye penetrant and magnetic particle on welds, wet fluorescent MT, and ultrasonic shear wave. Remove any leg of the triangle, material, environment, or stress, and SCC cannot happen. Erosion corrosion is flow acting as a grinder. When velocity gets high, the moving fluid strips away the protective film faster than it can reform. Fresh metal corrodes, gets stripped, corrodes again. It concentrates where the flow changes direction, elbows, T's, reducers, valve trim, tube inlets. The signature is directional, horseshoe-shaped grooves of bright, clean metal. Counter it with lower velocities, gentler geometry, or harder alloys, and inspect the outside of every elbow. Two hiding places deserve their own mention. Internal corrosion, the process fluid attacks the tube or pipe from the inside, while the outside looks brand new. And underside corrosion, tank floor plates resting on their foundation, wicking ground moisture, even from the soil side upward while the top surface shines. Both stay invisible until you look from the right side, iris and ultrasonics inside tubes, MFL scanning across tank floors, radiography on piping. And now the stealth killer, corrosion under insulation. CUI. The recipe: water gets past damaged cladding or open joints, the insulation holds it against the pipe like a warm sponge, and the pipe corrodes on the outside, invisibly, because the jacket looks perfect. The danger zone is roughly -4 to 175 degrees Celsius, worst between 50 and 120, and especially on cyclic, wet-dry service. Carbon steel rusts, stainless steel can suffer chloride stress cracking under the same wet insulation. CUI causes an outsized share of piping leaks, and nearly all of them are complete surprises. So how do you find CUI without stripping every meter of insulation? You target. Risk rank the lines, age, temperature, cladding condition. Strip windows at the likely spots, low points, dead legs, supports, penetrations. And screen the rest with tools that see through the jacket: profile radiography, guided wave ultrasonics, pulse steady current, and neutron backscatter, which finds wet insulation before corrosion even starts. Good cladding maintenance is half the program. Severity, then, is a number, not an opinion. Measure the wall at 2 inspections and you get the corrosion rate, here, 0.2 mm per year. Compare the measured wall with the required wall from design, and the difference, divided by the rate, is your remaining life. For pitting, the worst pit depth is what governs, compared against that same required wall. And for anything questionable, fitness for service assessment, API 579, tells you whether the remaining ligament can carry the load. Those numbers decide the next inspection date. The toolbox for assessing corrosion. Visual examination first. Trained eyes and good light still find the majority of problems. Ultrasonic thickness. Grid readings at established thickness monitoring locations. The pulse echoes off the back wall, and a thinner wall answers sooner. Profile radiography and guided wave screen piping and insulated lines without stripping. And corrosion coupons and electrical resistance probes live inside the process, so the fluid itself reports its own corrosivity, continuously. Combine periodic readings on the equipment with continuous monitoring of the process, and very little can surprise you. Prevention removes one element of the cell. Coatings and linings isolate the steel from the electrolyte, and surface preparation decides their life. Cathodic protection makes the structure the cathode, with sacrificial anodes or impressed current, so it cannot dissolve. Inhibitors and chemistry control build a protective film from the inside, filming amines, oxygen scavengers, pH control. And good design avoids the traps: the right alloy, full drainage, no crevices, no dead legs, no trapped water. Every defense is the same idea: break the cell. Pull it all together and you get risk-based inspection. Identify which damage mechanisms are active in each circuit. Assess their rate and their consequence. Inspect with the right method at the right locations. Evaluate remaining life, fitness for service where needed. Mitigate, repair, coat, upgrade, or monitor. Then repeat, with the intervals set by the measured numbers, not by habit. That is how you spend the inspection budget where the risk actually lives. The takeaways. Corrosion is an electrochemical cell, break any element to stop it. Know the form you're fighting, from uniform attack to pitting to CUI. Severity is a rate multiplied by time, compared against the required wall. Measure on purpose, UT grids, radiography, guided wave, coupons and probes.